I started my series of videos looking at epidemics and exponential growth. Fortunately now we are over the peak. The epidemic is retreating, but we do need to consider this serious issue of exponential decay. If we just plot the raw data, we can see the exponential growth phase in March, and then come April it's starting to be limited, and then we peak in early April, mid-April, and as we come into May we're falling nicely, but the curve does seem to have a slight tendency to turn left here. Okay, so we can look at the data in a bit more detail. If we plot it on a log graph, we can see roughly a bit of a straight line here. It was clearer when we looked at cases, because obviously in this period the UK was still doing a good amount of testing. Over here though, this actually looks more like a straight line, and those who know about it will know that a straight line on a log axis against linear axis means it's an exponential. If the straight line is going upwards, it's exponential growth. If the straight line is coming downwards, it's exponential decay. So we can look at the data from the 24th of April onwards, around here, and we can see that if we plot it, we can put a nice straight line fit with a very high correlation coefficient. But we do notice that the curve is slightly above the trend line here and slightly below in the middle. So then we've tried, using Excel, we can just fit an exponential curve to it, and we get an even more fantastic correlation coefficient. Basically, this is saying that the exponential curve explains over 99% of the variance in the data. There's just 0.6% of variance not explained here, whereas here it's 1.7%. So yes, the exponential curve fits the data we've been having really well for the last 25 days, since the 24th of April. Okay, so we can now plot those two onto a graph with the data back onto normal axes, okay, and we can see the dashed line fits pretty well, but the green curved line fits even better. So what does this imply? Well, first of all, if we use a linear model, it was implying that the death rate would go to 0 by the first week of June, and then it would be negative. So there's obviously a limitation there in the linear model. We have to stop it when it gets down to 0. And this is true for all models. We must bear in mind their limitations. So the reverse one here is the exponential decay curve, shows that we are reducing the number of deaths. We're halving about every 3 weeks. But we're not going to get down to half a case in 6 months' time. Okay, eventually it will either be 0 or 1 or 2. It'll always be integers. But we can see that, so what's going to happen is we're not rushing down towards 0 cases. Okay, we've got the exponential decay. Now, why would that be? Well, when the R value is less than 1, so let's take it to be 0.5, then one person infects half a person. Well, that's a bit awkward to do. 1,024 people will affect 512. 512 will infect 256. 256, 128. And so the numbers are halving each period, each half-life. If we go back to this graph, now these are my favourite axes, but slightly awkward to use. Okay, we've got the rate of death here up on the y-axis, and on the x-axis just the total number of deaths. Why is this my favourite axis? Well, exponential growth is again a straight line going upwards, and exponential decay a straight line coming downwards. So we have a straight line graph for exponential growth and decay without using logarithmic axes. Okay, so as I say, my first video I looked at the straight lines linked to here, but now we can look at the straight line here. Now, so we're looking here at almost 4 weeks of data, and we can see how fantastically well the linear fit is to it. Obviously, I've selected it when we've stopped curving, so it's a bit of a cheat, but still, no, an R-squared value of 0.9945 is incredibly high. So what's this model saying? This model is saying here, this graph is illustrating that we're heading towards a total value of 45,000 deaths. but that is only on these COVID-19 deaths being recorded from Johns Hopkins. So that's deaths where COVID is on the death certificate. We know there is a significant number of excess deaths where that's not the case, and so the total mortality rate is going to be well over 60,000. So I got to see this exponential decay was clearly happening in the death data. And then yesterday on the Downing Street briefing, I saw this graph and thought, I recognise the shape of this London curve. Notice London has had by far the most people in hospital, and it's been going away here nicely, and it's falling, but it's bending left. That looks like exponential decay, I thought. So now that they kindly provide all the data for us, I could plot it. There's their graph, and I've got the data, and we can see that, yes, I've got the right data. It's basically fitting the graph fully. So I can now look at the right-hand side of this graph from its peak onwards. Nice number of weeks there. I can do a linear fit. There we are. Same sort of pattern, illustrating that we are going to have actually exponential behavior being clearer. Again, fantastically high value of R squared. It's falling. Now, the amazing thing here is that the exponent here is almost identical to the one in the death data. In other words, we are again halving every 3 weeks. So I decided to plot the graph on logarithmic axes. Base 2. So you might recognize these as being the powers of 2. Okay, if you played the game 2048, you'll have got to this number, hopefully. And we can see that this curve here, this is all the data. We can see that since the 10th of April, 3 weeks later, it's down by a factor of 2. Okay, from the 24th of April, 3 weeks later, it's down by a factor of 2. It's exponential decay, and the half-life is 3 weeks. So this is telling us how the epidemic is being managed and going away during the period when we had full lockdown, though, remember? So I then decided to finally plot the data for our death data I've been showing you, the death rates per day against date on base 2 logarithmic curve. And again, we can see 3 weeks is the half-life period. Now, it hasn't been going on for as long as the hospital data, but still we can see, therefore, we're going to halve and halve again. So there's a crucial implication from this. When we look to the first week in June, when the government had been suggesting schools come back, we'd still be having not 0 deaths if we'd had the linear model, but 200 deaths a day. The epidemic would still be quite widespread in the UK. Do a full comparison. Let's compare that curve I've just shown you, this is from the FT now, with that for Denmark. Why Denmark? Because suddenly the government feels we should be copying Denmark. Unfortunately, we didn't copy Denmark in their rigorous lockdown a week before we did. So their peak was much reduced to ours. Notice, by the way, this is deaths per million. Yes, Denmark is a much smaller country than ours, but deaths per million was down a significant factor at the peak. They've actually only had about 600 deaths in Denmark altogether. So when is it that our death rate will be roughly similar to Denmark's at its peak? Well, we're still more than double. So it's about 4 weeks away. It's only when we get our values down much lower that really we can start comparing ourselves to Denmark and use the example of what Denmark did in their schools. In the meantime, perhaps we ought to consider countries more similar to us, such as Italy, which up until now we've been comparing with. Italy schools are not opening until September. Thank you for watching this video.